Hey everyone, so today's lesson is on symmetry. So half of what we're going to do in this lesson you probably learned in maybe elementary school or I don't know, sometime a while ago. But we're dealing with symmetry in two-dimensional figures. So symmetry in general is when there is a rigid motion, which is what we've been doing, reflections, translations, or rotations that map a figure onto itself. To map something onto itself, it just means that after you turn it or flip it or do whatever to it, it ends up looking exactly how it looked when it started, like the same orientation and the same location, like everything is onto itself. The first type of symmetry that we're going to talk about is called line symmetry, also known as reflection symmetry. And that's where one half of the image is the reflection of the other half. So this would be like if you folded it in half at somewhere in the figure, the sides would match up, the pieces would match up. So some figures will have multiple lines of symmetry and some will just have one and some will have none. So this is what the practice looks like for something like this. It says state whether the object appears to have line symmetry, write yes or no. If so, draw all the lines of symmetry and state their number. So the practice that you're going to do may look something like this. So for example, this crab. When they show you things in nature, you're kind of like, kind of assuming that it's the same on both sides. Like obviously in nature, like a crab won't be exactly the same, but that's okay. So this crab, we would say down the middle, that would be one line of symmetry. This starfish here, well, it definitely has one down the middle here, but then through each of its, I don't know what they're called, arms. I'm not really sure, but through each of its little arm things, so that's one line, two line, 3, 4, 5. So this starfish, we would say, has 5 lines of symmetry. This oyster shell is super irregular. Notice that this piece does not correspond to that piece over there. So we would say that the oyster shell has no lines of symmetry. There's nowhere we could draw the line and it be pretty much mapped onto itself. Number 4, the parallelogram. Oftentimes kids say that it has 2 lines of symmetry here and here. But if you were to actually fold this in half, But if you were to actually fold it in half, it actually would not have any lines of symmetry. So I know that may be hard to believe. I am going to see you in school this week, so I will show you in person that a parallelogram doesn't have any lines of symmetry. But try it yourself. Cut one out and try to fold it in half anywhere. Surprisingly, it actually doesn't have any. I know it looks like it might, but it doesn't. This pentagon here, 5-sided figure, there's one through this vertex. We could do one through that vertex and these sides would match up. One through this vertex, one through this vertex, and one through this. It's kind of like the starfish. There's one through each of its 5 vertices. So this one would have 5 lines. And then a rectangle, oftentimes kids say 4 because they think the diagonals would work, but actually the diagonals don't work. But it does have one down the middle this way and then one, and it kind of moved it for me, one that way. So this one would have 2 lines. So that's what line symmetry is. Pretty easy. This is the one that you've probably learned before, like when you were a kid. The next one that we're going to talk about is called rotational symmetry. So a figure has rotational symmetry if it can be mapped onto itself by a rotation between 0 and 360 degrees about the center of the figure. So I'm going to first show you visually what that looks like. So I have over here these 3 figures, and we'll pick this one first. So if I were to rotate this, do you guys see the gray outline of the shape? See how it says 16 degrees? So I can rotate this and it tells me how many degrees it is. So this would be considered to have rotational symmetry if I can rotate it some degree measure between 0 and 360 that would map it onto itself. That would make that gray be in the same position as the original blue. So notice that if I were to, too far. If I were to rotate this, see how it says 90 degrees? If I were to rotate it 90 degrees, see how it's mapped onto itself? The gray is on top of the blue, so you can't see the gray anymore. 106 degrees, 108, 10, whatever, is not mapped onto itself. But look, if I go again, another 90 degrees, so that's 180 degrees, it maps onto itself. If I go another 90 degrees to 270, it maps onto itself. And then all the way back to 360, it maps onto itself. So this shape would have rotational symmetry, again, because there are I could turn it 4 times before it goes back to the original. Something like this smiley face. Notice the smiley face turning the gray. I keep turning it and turning it. Okay, this is about 180. It's not mapping onto itself. It doesn't map onto itself until we're back to 360. So the smiley face would not have rotational symmetry. The sun, what do we think about this one? If I rotate the sun 45 degrees, it maps onto itself. Do we see the gray? So every 45 degrees, it maps onto itself. So 45 would be considered the magnitude. That's the smallest degree that it would map onto itself. It's like the increments. And then the order is how many times you turn it and it would map onto itself. So this one, the order would be, you just count like how many repeated patterns it has. So this one would have 1, 2, 3, 4, 5, 6, 7, 8. The order is 8 and the magnitude is 45. This one here has an order of 1, 2, 3, 4. See how this block piece is repeated 4 times? So the order would be 4 and the magnitude is 90. So going back to the note here, the rule is what we're going to fill in. That's a quick way for you to identify the order and the magnitude. Also, those are defined right here. I talked about them when I was showing you that other page, but the order is the number of times a figure can map onto itself as it rotates from 0 to 360. The magnitude is the smallest angle. So basically, to find the order, you just count the repeated patterns, like I said before, and then the magnitude I'm going to put here. The magnitude, you take 360 and you divide it by the order. And then again, the order, to find the order, you would just count the number. I always want to say like count the number of things it has, but that's obviously not very specific. So it just depends on what the picture is. If it's like this flower picture here, you'd count like how many petals. It's just, I say repeated patterns because it kind of covers everything. So count number of repeated patterns or repeated features or repeated, sometimes I say like distinct features. I never quite know the best way to word this, but I think you'll get the hang of it when we do the examples. So like this first one over here, do we see how we could split this into these 3 pieces? 1, 2, 3. So this like petal pattern is repeated 3 times. So it's not about line symmetry and how many lines of symmetry it has. It's about how many patterns it has like that are repeated. So this one has an order of 3. And then for the magnitude, you do 360 divided by 3, which is 120. So if I had this in that other tab, if I turned this petal 120 degrees, it would map onto itself. Okay, the Z has an order of 2. So there's like the top half and then the bottom half. 360 divided by 2 is 180 for the magnitude. This swirly picture, swirly, whatever this is called, has a magnitude. See how there's like kind of like this swirl, there's this one, and then there's this one. So this one has an order of 3. And so 360 divided by 3, again, is 120. This one has magnitude of 1, 2, 3, 4. This kind of like ninja star looking thing. You can split it into 4 repeated patterns. So like each corner is 4. Is one of them. So the order is 4. 360 divided by 4 is 90. So that's with just like random shapes. Down here, we're going to talk about regular polygons and how you can tell what the order and magnitude are. So first of all, a regular polygon, the word regular means that all sides and angles are the same. So this little trick down here only works when they're regular polygon. All sides and angles congruent. So like an equilateral triangle, obviously like all the sides are the same, all the angles are the same. A square, all the sides are the same, all the angles are the same, and so on. So what works for a square won't necessarily work for a rectangle because a rectangle is not a regular polygon. So for these, you actually can just count the sides for the order. So the repeated pattern is like, I guess you could think of it as each corner or each side, whatever. So this one has an order of 3. 360 divided by 3 is 120 for the magnitude. The square has an order of 4. 360 divided by 4 is 90. The regular pentagon has 5 sides, so that's an order of 5. 360 divided by 5 is 72 degrees. And then lastly, the hexagon is 6 sides, so it's an order of 6. 360 divided by 6 is 60 degrees for the magnitude. And so that's it. That's rotational symmetry. And we have line symmetry. So this is a pretty quick, easy section. Please let me know if you have questions. Remember that I'm available all day today on my Act Lab link. All right, have a great day.